Okay, welcome back. This is the last section I need to cover, 10.5 area now, and arc length, and polar coordinates. Okay, so we want to integrate these polar curves, and we can recall back to our Riemann sums. So we first are working with the area problem. So recall how that worked. So you would have some curve from some x values to some other x value, we'll say a to b. Okay. You would section it up into a bunch of rectangles. Okay. So this particular rectangle, say it's located at position x sub I. The width of that rectangle we would call change in x sub I, or we'll just call it change in x for the sake of sanity. This is a function f of x. We would have a way of figuring out the area from geometry is just base times height, right? The base is just change in x. The height will be f of x sub I. So the area of this ith rectangle should be f of x sub I times change in x. Right? And then to get an approximation of the area, we would take the sum of all of these little area increments. And then finally, to get the exact area, you take the limit as the number of those rectangles goes to infinity, or if you like the partitions going to 0, you can think of it that way. And you go from I equals 1 to n. Right? And then that gives us our integral for that particular case. And you see, you can always think of it as sort of height times base, and that was our integral, okay, as area underneath the curve. Now we have almost the same kind of construction. Now consider area underneath the polar curve. Okay. So our instead of having f of x, we should have something like r of theta. And instead of having a to b, we have like theta to theta. And then instead of change in x, we have change in thetas. And then our objects are going to be a little bit different. Instead of having rectangles, we'll have sectors of circles. So basically like pizza slices. And then we'll need the formula for the area of a sector of a circle, which is just what was it, like 1/2 pi r squared or something like that, right? So let's go at it and get a little picture going here. So here is our XY plane, and we have our polar system embedded on it. So I'm going maybe from some angle, we'll call it alpha, and then rotating over the some angle beta while our R function is tracing out this curve. Right? So maybe the curve looks something like this. I don't know. So instead of sectioning it up into rectangles, I'm sectioning it up into little pizza slices. Okay, so we'll have these tiny little slices of pizza here, which are basically just sectors of circles. And it's the same idea as this. We're filling it up with all these pizza slices. Dot, dot, dot. And then we'll take a generic pizza slice up here. And then dot, 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 all the way to this last pizza slice over here. So this particular pizza slice is, we could locate it at position, I should use a different color if I have one. Located at position, I didn't have a different color, but we'll call that theta sub I. Okay. Instead of x sub I, we have theta sub I. And then on top of that, the distance from here to the other side of the pizza slice will be called change in theta. Sorry, I had the right over that. It says change in theta is this distance. the function that's tracing this out, instead of some f of x, it's an r of theta formula. Okay, so we'll have some r of theta. The book will call it f of theta, though, but it's really just our radius function from before. So the book will call it f of theta. Right. So from before, we needed the area for a particular rectangle. And again, we're going to do that same construction. So I need the area for this particular pizza slice. See if I can find my red pen. I had a red pen. It's gone. Oh, there it is. So we want a formula for the area of this pizza slice here. Okay. And well, that looks real pretty. So the formula for the sector of a circle, if you recall from geometry or wherever you learned it, if you have a theta here, the area of this sector is going to be 1/2 theta r squared. If theta is 2 pi, you just get the formula for circle, pi r squared. Okay, so that's one way to remember it. So anyways, a sub I is going to be, in our case, 1/2. The r is going to be given from this function, so it's f of theta sub I squared, and then we'll use change in theta for this distance here, which is this distance here. Okay? So change in theta, or if you'd rather be less technical, you say change in theta sub I. I don't know if that's less technical or more technical, but I'm just remembering the way we generated the Riemann sum in this book. So anyways, yeah, that's the area formula. Again, we want to sum up all those areas, take the limit as the number of those pizza slices goes to infinity, and get a new formula in this context. So the total area will equal the limit as n goes to infinity of the sum of 1/2 times f of theta sub I squared times change in theta from I equals 1 to n, of course. And then limiting that, you get our formula du jour, 1/2 integral alpha to beta of your radius function, or f of theta squared d theta. Okay. We want to use that to find like the area of rose petals and area between polar curves and all that jazz. So let's go at it. First problem, number 7. We want to find the area of one petal of the given flower. So find area of one petal of r equals 2 cosine 3 theta. Okay, the easy part is just setting up the integral, right? The integral will be 1/2 from alpha to beta of 4 cosine squared 3 theta d theta. Okay. The hard part is figuring out the alpha and the beta. You gotta, I go and draw the thing. That's how I figure it out. I don't know if you got some clever way of doing it, let me know so I can pass it on to future generations. But for now, that's how I do it. I just literally draw it brute force and then figure out the bounds. Okay, so drawing this thing, then I have r equals 2 cosine 3 theta. The amplitude is 2. Then the period, I'm wedging 3 theta in between 0 and 2 pi. So theta will go from 0 to 2 pi over 3. Okay. Dividing this by 4, so 2 pi over 3 divided by 4 is the same as multiplying by 1/4. So I'm going by pi over 6s on my theta axis. So pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. And then if you need extra points, 5, 6, 7, 8 pi over 6, 9, 10, 11, 12 pi over 6. Okay? And of course we have an amplitude of 2. It's a cosine function, so it starts up and then goes down. Okay, so let's get the graph of this thing. I need two kind of concentric circles here. And then my little arms are going by pi over 6s. So I'll put those in red. So here's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, and then finally 5 pi over 6. Okay. So I'm just going to put 1 for 1 pi over 6, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pi over 6. And then we want to graph the guy. So we start at 2, start out here at 2, and then decrease to 0 at pi over 6. So we'll start at 2 and then decrease to 0. Okay, and then from pi over 6 to 2 pi over 6, it goes to negative 2. So it goes on this side out to here. So from pi over 6 to that, it'll go out to here. And then it'll go back to 0 at 3 pi over 6. So it'll zip in like that. And then from 3 pi over 6 to 4 pi over 6, it goes out to 2. 3 pi to 4, it goes up to 2. And then from 4 to 5, it goes back to 0. And then from 5 to 6, it goes to negative 2. So from 5 to 6, it's going out to negative 2. And then it's going to repeat itself. Okay, so we were able to draw it going from 0 to, I believe, 6 pi over 6. Okay? But the truth is, all we need to do is find the area of one particular petal. And there's symmetry involved here. We're not going to prove the symmetry. There's all kinds of, just like when you're doing even and odd symmetry, you can put like negative x in. And if it's f of negative x is equal to f of x, then it's even symmetric. You do the same baloney here. They have the same kind of tricks. We'll just presume it's symmetric, though we don't have time to go through all that. So if it's symmetric, then all I have to really do is find the area of half of it. So I can basically integrate from 0 to pi over 6, but multiply it by 2, right? So my end integral then will be 2 times 1/2 times 0 to the pi over 6 of our r squared, which ended up being 4 cosine squared of 3 theta d theta. We can figure that out. 2 over 2 is 1, so I have a constant of 4 sitting out in front. Use your half angle formula to rewrite cosine squared as 1 plus cosine of 6 theta all over 2. And then 4 over 2 is just 2. Integral of 1 plus cosine of 6 theta d theta. And then, of course, that will be 2 times theta plus sine of 6 theta all over 6, evaluated from 0 to the pi over 6. So that'll equal 2 times, putting in pi over 6, sine of 6 times pi over 6 is a sine of pi. Sine of pi is 0, so that will be 0. And then you plug in 0 into these, you get 0 again. So it's just 2 times pi over 6. In other words, it's pi over 3 for your final answer. Yay. All right, let's look at finding the area of the inner loop of this, I think it's a lemison. Okay, so this is problem 19. Find area of inner loop of r equals 1 plus 2 sine theta. Okay, so first I'm going to graph that thing. It has an amplitude of 2. We're cool with the period, right? This 1 will shift it up 1. So shift up 1. And the period is just the traditional from 0 to 2 pi. So my take marks take that 2 pi and divide it by 4. And I'm going by pi over 2s. Okay, so the picture then, so originally it's sine function 1, 2, 3, 4, so it would be like this, and then it's being shifted up by 1 position, so its new sort of origin is this line, and we'll be going up to 3 now, so our graph will look like this. And then it goes down to 1 right there. Okay, I needed the polar version of this thing. I need like 3 circles here. 1, 2, 3. And then I'm going to draw this guy in red. So I start at 1, and then from 0 to pi over 2, it's increasing out to 3. Okay, so at 1, and then it has that curvy kind of feel to it. It increases out to 3, and then it's decreasing back to 1 at pi. So this is pi over 2, this is pi, 3 pi over 2, and then 2 pi. So it'll decrease back to 1 at pi, and then it's decreasing even more, and eventually it'll go to 0 as it hits this point here. So it'll decrease even more until it goes to 0, and then it starts going negative to -1. Okay? So that's where the inner loop is going to happen. It's going to start happening here, and then it'll reach its sort of maximum right here, and then it'll fall back to 0 in this direction, and then increase back to 1. Okay? So it's this that I need a formula for, or sorry, I need to do an integral for. I need to find the area of that thing. Okay? So it kind of looks like a spinal column or something. Maybe you can model spinal columns using these. Right, so a vertebrae with a spinal cord going in it or something, I don't know. So anyways, I'm going to be integrating basically from here to here. That'll give me this part of the curve. Okay? And we need to figure out what those are. So what are those? Well, those are the places where the r function is 0, right? So it's where this is equal to 0. And so on the integral from 0 to 2 pi, I need to solve this equation, 1 plus 2 sine theta equals 0. And so 2 sine theta equals -1, so sine theta equals -1/2. So theta, the reference angle for 1/2 is pi over 6, and then sine is negative in the 3rd and 4th quadrants. So I'm looking at 7 pi over 6 and then 11 pi over 6. So not the prettiest of numbers, but those are they. Okay. So my integral then will be 1/2 integral from 7 pi over 6 to 11 pi over 6 of the square of this r value. So it'll be 1 plus 2 sine theta squared d theta. This one is a bit of a monster. I'm just going to save my sanity and leave it at that. And you can evaluate it on your own. Okay. All right. The next section then is finding intersection points of polar graphs. So points of intersection. And this is important for finding the area between curves. If you recall, maybe you had some sort of, I don't know, some kind of like sine curve. Let's draw it like this, going up and down and up and down. Okay. And you wanted to find the area between that curve and this curve. Okay. So the problem with that, and let's presume, okay, there's obviously symmetry is involved, but let's presume we didn't have that symmetry. So maybe these curves are doing something funny up and down. How would that integral look? So if this is A, B, C, D, E, you would have, and let's say the red curve is g of x, and the black curve is f of x. Well, if these points weren't given, you would have to find those points of intersection, right? So to find the points of intersection, you would set the equations equal to each other and solve. Okay. And then once you get that, you can set up your integrals. So first I'm going from A to B, and in that case, the guy on top is the black guy, the f of x, and then the guy on the bottom is the g of x. So it would go f of x minus g of x dx plus the integral from b to c. And you have to use a different integral because now the g of x, the red guy, is on top, right? So it would be g of x minus f of x dx. And then that would carry on, right, dot, 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 plus to your last integral, where g of x is on top and f of x is on the bottom. Okay, we're going to do basically the same thing now, but in polar coordinates. So I'm going to give you an example. And I don't know, so let's try this curve. So somehow we were able to generate this curve. That'll be g of theta, and then another curve, right? And we'll call that one f of theta or something. Okay. So in order to do this guy, I need to know the intersection points for my angles. So maybe this is theta alpha 1, this guy is alpha 2, this angle is alpha 3, etc., right? So this is alpha 4, this is alpha 5, alpha 6, alpha 7, alpha 8. Okay. And then again, the red curve, let's make the red curve like above, is g of theta, and the black curve will make f of theta. And let's say we want to know the area, how do I want to do this? These areas here. Okay, so I want to know, you have another color here. I want to know this area. Etc. It's like all of these things. Okay, so it's kind of the same problem as up here, where I'm trying to find the area inside of these things. Or maybe let's find the area inside this weird star thing that's going on the inside. So this is the area I don't want. I'm coloring in pink. And then I'm just going to look for the area inside that star. I guess we could put that in green or something. I have a green pencil. Using all my colors today. So yeah, we want to find the green area, let's say, instead. Okay. So to find the green area, you're basically doing the same thing you did up here. You're kind of identifying which is on the top and which curve is on the bottom. In this case, it's always going to be the curve that's on the bottom, I guess. Well, you wouldn't even have to do differences. So let's do the pink area. So the area of the pink stuff, if you're just finding the area of the star, you would have to change. So for the pink, we could do both, I guess. The pink would be of course, 1/2 times the integral from alpha 8 to alpha 1, and in this region, f of theta is on top of g of theta. So to get the pink region, you're going f of theta minus g of theta, and it's going to have each one so each one of these guys should be, and of course I don't have an example. So you're finding the area underneath 1 and then subtracting away the area. So it must be f of theta squared minus g of theta squared d theta. Okay. So that would be this pink region, and then from alpha 1 to alpha 2. And in that region, the g of alpha, g of theta is on top, and f of theta is below. So it's the area in here minus the area right here. Okay, so it's going to be this time g of theta squared minus f of theta squared d theta. And you keep on going on and on until you get to the 1/2 integral from theta alpha 7 to alpha 8 of so which one's on top? Then g of theta is on top minus the f of theta on the bottom. Okay. Let's not do the green one. Well, yeah, sure. Let's do the green one. The green one then, for the green area, it's a little easier because you're just picking which particular curve you need to be basically on top. You're finding the area underneath this curve from alpha 8 to alpha 1. So you need only use one function. Okay? So to get this area here, what would you do? You would have, so for the green, which I just colored in black, you would have 1/2 integral from alpha 8 to alpha 1 of, in that case, the curve that's telling me what this area is. If I did a bunch of little pizza slices, the tops or the lengths of the pieces of pizza would be given by g of theta, not by f of theta, which would be way out here. Okay, so you would just have g of theta squared. So it's much easier in that case. And then plus, in this region, from here to here, this little wedge that we're after, this junk, is given by the black curve. So the f of theta that time, when I'm going from alpha 1 to alpha 2. So that would be f of theta squared d theta, and so on and so forth, right? Plus dot, dot, dot. Okay, so that's the idea. It's parallel to what you already have done. It's just instead of saying what's on top and bottom, you're kind of moving in the pizza method. So the top of the pizza is right here, and then the bottom, the corner, the pointy part of the pizza is the bottom of the pizza. Okay, so you want the top curve, the crust, minus this bottom curve, which is towards the front. Okay, something like that, right? Anyways, let's move on. Phew, beat that to death. The first issue is finding then those intersection points, right? So the intersection points are kind of weird here because of that negative issue. You can't just, okay, so what's the problem? Let's look at number 39. R equals 4 sine 2 theta is one of our curves, and then R equals 2 is the other. So the issue is, you have satellites. What the book says, you have satellites orbiting the Earth, and their orbits themselves may intersect, but the satellites will never hit each other, right? So you have the Earth and the satellites are zipping around the Earth. So maybe here's one satellite, right? And then you have another satellite, maybe it's going like this, and the actual paths of the satellites will intersect each other, but the actual satellites never hit each other. Okay, that's kind of the issue that's going on here. So when you solve for the intersection points, you may have a little bit more work to do. And again, I would kind of advise just drawing the things and kind of figuring it out from there. In this particular example, to get the intersection points, you just take the two expressions and set them equal to each other. So 2 equals 4 sine of 2 theta. In other words, we're looking for where sine is equal to 1/2. The reference angle for that would be, in particular, then, what is it, pi over 6. And then plus, so are there two? Yeah, there's 2 of them. So 2 theta is pi over 6, and 2 theta is pi over 6 plus a 5. Where is sine positive? So sine's positive in the second quadrant. So that would be 5 pi over 6 plus 2 pi n. There we go. The slow horse crosses the finish line. All right, so pi over 12s plus pi n's, and then theta is 5 pi over 12s plus pi n. The problem is this won't give us all of the intersections, and we don't know it yet, but I believe we can trace this curve going from 0 to 2 pi. Maybe we should actually do that just to be careful, because we only want solutions that will be on, we don't want repeat solutions. So let's figure out the curve, and then we'll come back to this and kind of identify potentially all of the intersections, but you'll see that we don't actually get them all. And it's because the R value will actually be kind of negative on this thing. And so instead, this thing will be equaling -2 sometimes when it's actually hitting the circle. So you won't get equal to 2, you get -2, and therefore you won't pick up those points. But let's take a look at it. So R equals 4 sine of 2 theta. The amplitude is 4. Right? The period then, we're wedged in 2 theta in between 2 pi and 0. So theta is in between pi and 0. Chop that up into 4 parts. So our tick marks, or our little helper lines, will be at pi over 4s. Okay. So let's first draw this thing in the r theta plane. 2, 3, 4, 2, 3, 4. And we get pi over 4 is 1, 2, 3, 4 pi over 4, 5, 6, 7. We'll just go out to 2 pi. Right? So the sine function looks like this. Right. Okay. So what? Let's go to our xy plane then. And we need some concentric circles for this, so I need to go out by 4. Right, and then I'm going to graph this thing in green. Oh, I need some helper lines. We put those at pi over 4s from this. So pi over 4 is 45 degrees. So it goes right through there. This is pi over 4. And then I'm just going to write 2, 3, 4. Right, so when theta is equal to 0, r is also equal to 0, and then it's going to increase to 4 at pi over 4. So it's increasing to 4 at pi over 4, so it's going to give us this kind of pedal. And then it'll decrease back to 0 at pi over 2. Right? And then from pi over 2 to 3 pi over 4, it's going -4. Right? And then from 3 pi over 4 to pi, it's going back to 0. And then from pi to 5 pi over 4, it's going out to 4 again. And then it's going to go back to 0. And then it's going to go back to -4. and then it's going to go back to 0 again. Okay? So get this four-leaf clover thingamajig. The graph of r equals 2 is just a circle with radius 2. Okay? So we can graph that pretty easily. Let's put it in green if I can find a green pen. So that would be right here. And yeah, we were able to graph it out from 0 to 2 pi. Okay. So our points of intersection, we're looking for the ones from 0 to 2 pi. So the first theta pi over 12 will work. That's in that interval. Plus pi over 12 plus 12 pi over 12 will give me 13 pi over 12. And then if you add in another, oops, so pi over 12 from when n is 0, and then when n is 1, you get pi over 12 plus pi, which is pi over 12 plus 12 pi over 12, which is 13 pi over 12. But if you add in then another 12 pi over 12, you get 25 pi over 12, which shoots you out of our interval. Okay? And then from these formula, 5 pi over 12 is one of the angles. So 5 pi over 12. And then plus another 12 pi over 12, so that would give me 17 pi over 12. But then if you add in another 12 pi over 12, you go out of the range again. Okay, so this is the only 4 intersections that the equations are actually giving us at this point, which is a bummer, because if you look at this graph, there are 1, 2, 3, 4, 5, 6, 7, 8 intersection points. So we missed out on 4 of them. Okay? So the deal is it's not picking up those places where this thing is equal to, and for instance, -4, or rather -2 and -2. So it's missing this one and this one in particular. So it picks up this one, and then misses this, and then picks up this one, and then misses this and this. Okay, so I need to find those points in particular. Okay, and we could use symmetry to do that. We're not going to have to do anything crazy. I mean, you could literally set this equal to -2 and pick them out, but let's just use symmetry in order to pull this off. So this first one here is the pi over 12. Okay. And then I'll go to here. And so by symmetry, you know, if this is pi over 2, that's the same as 6 pi over 12. So this guy must be 5 pi over 12. So there's a 5 pi over 12. Okay. And then from here to here, by the same logic, this is 6 pi over 12. This will give me 7 pi over 12. Okay. So right here would be another intersection. And then I need this guy, which would be right before 12 pi over 12. So that would be at 11 pi over 12. And then I need this guy right here, which I think I already have, right? So this, no, that would be, yeah, that would be the 13 pi over 12. And then I need this guy right here. So if this is 3 pi over 2, that means 18 pi over 12. So one before it would be the 17 pi over 12, and then the one right after it would be, well, 18, 19 pi over 12. So that's another one I'm missing, and that'll give you all of them. Okay? So those will be all of our intersection points. Okay. So what does the book want us to do then? The book wants us to figure out the area of that's in common with the rose petal and the circle. So it's this kind of like a 4-leaf clover, but somebody went out and then took a pair of scissors and cut off all the leaves, like right here. You know, we want to find the area of that. So maybe in reality, you could be modeling a propeller of some sort. Okay, so I've seen them use polar graphs in modeling in airplanes. Actually, I think they were using hyperbolic graphs, but oh well. It kind of looks like a propeller, right? We need to find the area of that, and that's our goal here now. So I needed those intersection points for the limits on my integral in order to figure out those areas. I'm going to zoom in on just one particular quadrant. Okay. So here I go. And I'll have, let's look at, there's one circle, and then here's two circles. And I'm going to run out of room. So here's one, cheat, two, and then three, and then four, right? So the rose petal curve is hitting its maximum in this quadrant when we're at pi over 4. Okay? So it's going like this, and then curving into that. The circle is right here. And then it'll come back around. But we're going to use symmetry to kind of figure this out. I'm basically going to find the area in this region and then use symmetry and multiply it by 8 to get this area, and then this area, and this area, this area, this area, this area, this area. So it'd be times 8. Just find this region and then multiply by 8. So to find this region, it's that what is the crust of the pizza and what is the tip of the pizza kind of problem. So in this particular case, then, I don't know how we're going to do this. There's actually kind of two regions to consider. This first region here, which I'll put in green, and in that region, the crust of the pizza is given by the flour curve. Then in the second region, from this angle alpha to this angle pi over 4, the crust of the pizza is given by the circle. So I'll put that region in red. Okay. So I need basically two integrals, one to handle the green region, one to handle that red region. So for the green region, I also need to know this alpha value, and that's the intersection between the rows and the circle. So I know that alpha, I found it, it's pi over 12. Okay. So my first integral is going to be 1/2, and I'm going to go from 0 to pi over 12 of my r function squared. And my r function was 4 sine 2 theta squared d theta. And then I'm going from, for the red part, it'll be 1/2 integral from pi over 12 to pi over 4 of the r function. This time it was just that r equals 2, so we have 2 squared, and then d theta. And then finally, I need to multiply all of this by 8 to get my total answer. Okay, and that I'm just making sure I wrote it up right. That does it pretty much for the area part. We still need to again work with arc length. So another arc length formula then, and then this will kind of do it for us until next time. Arc length. So this formula, again, you can kind of back engineer it if you know the parametric form for the arc length formula. you can just replace, but I'll just give it to you straight off for the sake of sanity and time. It's going to be f of theta, which would be your r of theta squared, plus f prime of theta squared d theta. So problem 57, they give you r is equal to 4 sine theta, and we want to know the arc length from 0 to pi. Okay, and pretty easy. I need r prime, so r prime is 4 cosine theta, and then plop it into our formula. So s is equal to the integral from 0 to pi of the square root of 16 sine squared plus 16 cosine squared, which is just 16 d theta. So the square root of 16 is 4. The integral of 4 is 4 theta from 0 to pi. That's equal to 4 pi. Okay. So that'll do it. We'll see you next time, or we'll see you in the next course. Bye-bye.